哎呀，热播吧，咱记录一下。阴天打孩子，闲着也是闲着。啊，今天洗个澡，10点。按理说是可以早睡一下的。妈的，过去3天，包括今天，搞这个涂鸦力，终于给他搞得差不多了，应该应付周3小考应该没啥问题。所以说我现在还欠一个上周的 engineering， 我那个没看，我忘了看了，我今天才想起来。我说这进度的感觉快了这么久了。然后还有一个是今天的3009也没看，我操！那明天早上直接就3009那个 practical，明天早上早起一下，我直接给他怼了。然后数学也没看，没做，妈的！哎，行吧，先把这个弄完了吧，这1个小时先把这个4001给进度搞齐了。
But yet, what we're doing is we're not calculating these stresses or this effective stresses, friction angles, etc. We're saying this is actually equal to some number equal to SU. Now, how do we make this equation here equal to this equation here? And what we do is we set C dash equal to SU, and we set phi dash equal to 0. So if we do that, you substitute into the more coolant equation, you get tau F equals SU. You're not actually saying the friction angle is 0 or the C dash value is SU. You're just using the same algebra that was used to develop the equations for active and passive limits, but by actually but by using those equations and making this substitution, we're actually solving for the problem when tau F can be defined as a simple number equal to SU. So for example, we write down our equation sigma HA equals sigma HA dash plus U, and say that's equal to Ka times sigma V minus U minus 2C dash root Ka plus U. Now, when phi is equal to 0, Ka is equal to 1. And you can think, for example, 1 minus sine phi over 1 plus sine phi for the Rankine case is equal to 1, because the friction angle would be 0 in that case. So we then come back to this equation here. We say sigma HA is equal to 1 times sigma V minus U minus, now C dash will be set equal to SU, so it's minus twice SU times the square root of 1 plus our water pressure plus U. From that, we get an equation, U's actually cancel, so we get the equation sigma V minus twice SU is the total stress acting on the retaining wall when you've got active conditions.
Say it again?
Plus our water pressure. From that, we get an equation, U's actually cancel, so we get the equation sigma V minus twice SU is the total stress acting on
total stress horizontal active
on the retaining wall when you've got active conditions. About calculations of the water pressures when you're looking at undrained conditions in clays, you can calculate the total stresses acting on the active side of the retaining wall by looking at that simple equation. Vertical total stress minus twice the undrained shear strength. And similarly, you can show that sigma HP, that's the maximum horizontal stress acting in undrained conditions on the passive side of the retaining wall, is sigma V plus twice SU. So that makes life quite easy when you're actually doing your calculations. You don't.
What 什么意思在这搞？
Don't have to think about what the water pressures are, and you've got a simple equation to go and determine the value of your stresses, active and passive. Now, there is one additional point we need to make, that if sigma v is less than twice SU, and sigma v, we call sigma v is equal to, say, gamma times h. So that would be the unit weight of the soil times the depth h. What we would find is that you substitute into this equation here, and you would get a negative number. Just write down here for your notes. That implies sigma h is negative, and which it can't be. It can't be negative because if you can imagine a wall, soil up next to a wall, and the wall is moving away from that soil, what a negative number would mean that the soil is actually trying to pull the wall backwards, and there's no way that's going to happen. So what happens is you end up getting a crack forming in the soil, and those stresses are dropping to zero. So what happens? It can't be. So we end up with a crack forming in the clay, and the crack would form to a depth, equal to twice SU over gamma. So if you look back at this equation here, if sigma v was equal to gamma h, when gamma h is equal to twice SU, you're just back to the 0 point. When gamma h is less than twice SU, then you've got a negative number. So probably draw this for you now. Let's do an example. So you've got a wall here maybe, and you've got clay here on this side of the wall. And what will happen is that when we've got this situation where the sigma HA value turns out to be negative, you'll end up with basically large cracks occurring in the clay behind your retaining wall. And that means when a crack forms, there's no pressure within the crack, and the stress is dropped to zero. So this is a critical, I call this H crit here, is twice SU over gamma. So this would be the actual depth of the crack that would form. And it's not anything complicated. It just means that when that's forming to a depth at which, when this expression for sigma HA works out to be a negative number, and that actually, that's where you get crack forming. So in this situation, you end up with no horizontal stress on the wall. So I'll just write this down, over depth of H crit, there's no horizontal stress on the wall. And that's why, for example, if you ever see a clay material, you can actually dig a vertical cut in your clay without any retaining wall, and the actual vertical cut remains stable. And that's because at that situation you've got high underlying shear strength. It's much higher than the vertical stresses in the ground, and you end up with just a vertical face of clay which is completely stable. So you don't need any wall, for example, to provide rotation to it. Another, I suppose, point that needs to be borne in mind is that after a period of time, you might get rain filling up the crack. So this could now, you could get rain forming here, in which case the stresses increase from 0 to gamma W times Z, where Z is the depth. over for z, for z greater than less than h. So you can get a crack forming, definitely, but you could imagine that that crack can actually fill with water, in which case you need to allow for the fact that there's an additional stress. So to summarize, what you can say is sigma HA is equal to the maximum value of, to summarize, so you can get a crack forming, definitely, but you could imagine that that crack can actually fill with water, in which case you need to allow for the fact that there's an additional stress. So to summarize, what you can say is sigma HA is equal to the maximum value of sigma V minus twice SU, or gamma W times Z. So under the active conditions of what we're saying is that we can get, you should, for your design situations, when you find this is negative, obviously it's going to be 0, at which point you need to use gamma W times Z. Otherwise, you can use this equation here, sigma V minus twice SU. The maximum of those two numbers is what, just in simple terms, is what you can actually use. In reality, you can get, once this term is positive, then that's actually the number of the stress that you would use. But many designers would also assume that this value is the minimum stress acting in the wall. Okay, so that's, but largely, this is the important equation to remember to work out what the active stresses are on the retaining wall in run-rate conditions. So the next thing we need to bear in mind, so that was looking at undrained conditions. The next feature we need to look at is when we've got seepage under a retaining wall. So if we have a retaining wall that looks like this, and just for simplicity, we'll say the water table is at the ground level. Now after a long period of time, you'd imagine your water on the excavation side of the retaining wall is going to end up, and you're going to have equilibrium where the water level rises back on this side of the retaining wall. So you do an excavation, and if you left it, you would find that the water level would return back to this level. Essentially, that's a fully equilibrium situation. However, that's completely impractical for building a basement. So normally you have some sort of a drainage trench with gravel, and you basically got a pump connected in with that pipe to actually keep the water level down so that you can actually construct your basement. So what's happening in this long term, in this situation, is actually you're getting steady seepage of water around your retaining wall. And that volume of water that's seeping under the wall is actually being pumped away to allow you to keep the water level down at this point. Now most of you have already done geomechanics, and I believe you've already covered things like flow nets. So you would imagine you've got some kind of a flow underneath a wall like this, and you would have equipotentials, something like that. To give us, and if you remember what those equipotentials mean, it tells you, well, what is the stress at any point within our mesh or problem area. So what we're saying is we're getting flow lines. These are flow lines here, and along each of these equipotentials, we're getting the same amount of head loss between here and here, between here and here, here, etc., as we go around the retaining wall. Now, what's happening is that the head loss, we call this number H. As the flow line goes around from one side of the wall to the other, by definition, we're at this height here, at this side of the wall, but we've lost this height here as we travel around the actual retaining wall. So the water pressure at any point will be the hydrostatic water pressure, plus the water pressure that's remaining after the water, as the water, after discounting the amount of water head loss as the streamline passes under your retaining wall. In terms of typical seepage reservoir here, in terms of a typical retaining wall calculation, we can make the problem a little bit simpler. And in page 54 of your notes, there's this example here. which instead of drawing a flow net, we're just looking at drawing one streamline that's flowing down one side of the wall and back up the other side of the wall. And this sometimes takes a number of students some time to actually think about, to understand what it is, but once you do think about it and understand, then it's pretty easy after that. So what we've said here is as we go from this side of a retaining wall to this side, we lose an excess head of H. So progressively we're losing an excess head of H as we go down and go around this path. So over the path length, which is what's the path length of this streamline that's running down the front of the wall, down the back of the wall, up the front of the wall, it's H plus A plus A. So over a distance of H plus 2A, we lose an excess head of H. So when we're down at the base of the wall here, we have lost an excess head equal to H plus A over H plus 2A times the excess head that's present. 2A, H as we go down and go around this path. So over the path length, which is what's the path length of this streamline that's running down the front of the wall, down the back of the wall, up the front of the wall, it's H plus A plus A. So over a distance of H plus 2A, we lose an excess head of H. So when we're down at the base of the wall here, we have lost an excess head equal to H plus A over H plus 2A times the excess head that's present. Now, when we look at the bottom of a wall, there's obviously, if you go 1 millimeter to the side on the left-hand side of the wall to the other 1 millimeter to the right-hand side of the wall, it means we've actually got, we can't have a different pressure there. We've got the same pressure at the base of the wall. So what we normally do is we try and assume, first of all, calculate what that pressure is at the base of the wall, and then we can assume a linear distribution, as I'll show you in a second. So when we're down at this point here, we have the proportion of excess head that's left is equal to whatever's left of our streamline length, which is A, divided by the total streamline length over which we've lost the excess head. So it's A, this value, divided by the overall length, H plus A plus A. So the remaining excess head at the base of the wall here is going to be equal to that number. And then to work out what the water pressure is then, we look at we just multiply by the unit weight of water to give us that value of excess pressure. And then we need to add the static head, because at this point here we're at a depth A below the water table here. So the static head is going to be gamma W times A, and that gives us our water pressure at the base of the wall A. That's an important calculation to understand. Now, once we've done that, and that gives us our water pressure at the base of the wall A, and that's an important calculation to understand. Now, once we've done that, we calculate, typically in a typical problem, we will calculate this water pressure at the base of our wall, and then we will assume a linear increase of
success.还有这边的水压，加上一个 它这边水压了。损失掉了 HA。对，这个要加上。那为啥不加 HA？
excess pressure, and then we need to add the static head because the static at this point here, we're at a depth A below the water table here, so the static head is going to be gamma W times A, and that gives us our water pressure at the base of the wall A, and that's an important calculation to understand. Now, once we've done that, what we then we calculate typically in a typical problem, we will calculate this water pressure at the base of our wall, and then we will assume a linear increase in water pressure with depth corresponding to that water pressure at the base of the wall. Now, when you do that, you'll find the actual profile or gradient of water pressure distribution here is less than hydrostatic on this side of the wall, and it's greater than hydrostatic on this side of it. And that's because we've got a seepage situation. We don't have a static water pressure distribution. We've got this. And essentially, if you look at this, what it's really saying is, well, we can't. I've got water on one side of the wall, much higher than on the other side, but I'm the same pressure, at this point. So I'm obviously somewhere in between the water pressure corresponding to this head of water and this head of water, and that's why we end up with different gradients. Now this is an example just for illustration of this equation here, and just putting in numbers into that, and what we find at the base of our water wall here, we find for this excess head of 8 meters, we've got a water pressure of 72 kilonewtons per square meter, and we've got we can calculate the actual water pressure gradient at any point, which means that what am I calculating the gradient as?
non-homogeneous.
Just write down here, just the gradient and water pressure gradient. Gradient on the left-hand side is equal to 72 divided by 13.
意思我操！梯度吗？
And on the right-hand side, it's equal to 72 over 5. So if we wanted to calculate the water pressure at this point here, say at Z equal to 8 meters, our U value is going to be 72 over 13 times 8 is the water pressure at that depth here. So it's just giving you a different way of calculating what the water pressure is. And when you've got secret, you can't use this hydrostatic value. You can't assume you've got hydrostatic conditions. You have to use that revised gradient. Now there is, if you look at the gradient on the right hand side of the wall here is greater than the actual water pressure, the hydrostatic case, and there's a situation can arise where that gradient can lead to effective stresses in the ground which are actually zero. So, and that there's one other calculation which is very often asked in exams and in problems is to find what the factor of safety is against what that's called piping. So when you get piping or liquefaction, boiling, there's three terms that are used in the literature. It's when sigma v dash is equal to 0. Now, that means the overall strength in the ground has disappeared because the effective stresses are not are 0, and we know from more Coulomb equation when the effective stresses are 0, then we've got no shear strength. So what would happen is it's like quicksand is another word for it here. You'll end up with potentially the ground on this side of the retaining wall turning into quicksand. So the sigma v dash of 0, when does that actually happen? So I'll write down your notes. Factor is equal to the vertical total stress at any location divided by the water pressure. And normally, say at the base of the wall,
上哪儿鸡巴来了6啊！我操！
in the particular example we had, is equal to 6 times, I think the unit weight was 19, and the water pressure at the base of the wall was 72, and that gives you 1.6. So that's exactly the same calculation written down here. So if your factor of safety is less than 1, obviously sigma v in that case will be less than u, and you're going to have a piping situation. So if that factor of safety is close to 1, obviously you've got an issue, and you've got very low strength in the soil next to your retaining wall. So that's in a kind of an aside, because what will happen, when you're doing your calculations for vertical effective stress on the passive side of the retaining wall, you'll be using the gradient of water pressure distribution on the right hand side to go and determine what your water pressures are. So, for example, and it's going to be greater than 10, so it might be quite a high number, and you're going to end up potentially with quite low vertical effective stresses. Even if you don't have a piping situation, you might have a failure because you've got very low passive resistance because your effective stresses, remember your effective stresses are sigma v minus u, and we'll look at an example just illustrating this, they could drop to quite low numbers, in which case the wall might actually fail. So it's like everything. Just two examples of two aspects of that we have just been talking about in terms of the undrained conditions in clays and the seepage around the retaining walls. The very often the best. Best kind of understood by doing a few examples, and we'll do plenty of examples, and I'll also put some more examples on the LMS. And we're going to probably spend more time. We're going to do a series of examples, and I'll do a couple now in a minute, and then we'll do some more examples over Wednesday, just going through various calculations. But first of all, I want to just put it in context. Why are we doing this? And I think I probably told you already that nearly every construction in urban environments these days has a basement of some form. So-called embedded retaining walls. That's a critical. These are steel sheets which are hammered or vibrated into the ground, all interlocking to form a retaining wall as indicated here. And just as I've already talked about in the context of your lab 1, for example, this is called a cantilever because it doesn't have anything supporting the retaining wall above the excavation level. So you can imagine that if you're thinking in terms of structures, it's just on its side, or if you switch that around, you've got to extend it on a cantilever. And it's assuming some point of rotation, and the wall is rotating about some point at a location O at some point in depth. We'll look at that in a second. So that would be a typical cantilever wall. Very often, this might be an example of a propped cantilever. Well, it's actually called a propped cantilever. It's actually a propped retaining wall. This is maybe how you might construct a jetty, constructing a whole load of sheets together on either side. There's some sheets here, and there's sheets here, and the slab at the ground level is actually propping those together. These are, this is no site. This is Elizabeth Quay Station, but an example of when they were building Elizabeth Quay Station. These are steel sheet piles which were 35 meters in length, hammered into the ground, and this kind of structure here is there to provide some guidance to actually the sheet piles as they're being installed. When you're building a bridge and sort of foundations for a pier in a river, for example, you often construct a cofferdam, which is a whole series of sheets constructed in a sort of a circular or in a square configuration. You install that in the middle of the river, say, then you pump the water out from within inside that sheet piles, and then you in a sort of a circular or in a square configured foundations for a pier in a river, for example, as they're being installed. When you're building a bridge and sort of a pier, foundations for a pier in a river, for example, you often construct a cofferdam, which is a whole series of sheets constructed in a sort of a circular or in a square configuration. You install that in the middle of the river, say, then you pump the water out from within inside that sheet piles, and then you construct your base for your bridge pier in the middle of the river. So that's called a cofferdam, and these are again steel sheets which are used for that kind of work. Diaphragm walls, these are concrete walls which are used extensively around the world for building large deep basements. So, for example, all of the new currently underway or just completed the diaphragm walls for the airport stations, the 3 new stations for the airport link in Perth, for example, have large diaphragm walls. There's more diaphragm walls went in on Canning Highway, just near the Canning Bridge, for example. Lots of examples of large concrete walls, so they're not necessarily steel sheet walls. That's an example, for example, of a diaphragm wall or a concrete retaining wall. And I'll talk about these are anchors here, which are causing restraint to the top of the concrete wall. Again, to that again. This is more examples, but that's where the BHP building is now. These are again old ones. This is where you could construct a circular excavation using, this is very often the kind of technique would be used when you're building a tunnel. You would drop your tunnel boring machine into your excavation, which would be constructed maybe in a manner like this. More commonly in Perth, for many 2-level or 3-level basements, the embedded retaining walls which are used are a series of piles all constructed alongside each other. So these are reinforced concrete piles and all installed together, and they form one wall. And obviously, all of these walls, it's important to realise, are installed before you do any excavation. You're not coming along to your site. These are installed, and then you proceed with your excavation. These are anchors here, which I'll talk about again in a second, to actually provide some restraint, and they will change the mode of failure or mode of deformation of your retaining wall. Instead of using these are anchors which are installed from within the excavation. They extend outwards and provide some reaction that will pull back the wall. You can alternatively install some propping internally like this. This is like a bird's eye view of the site. We've got these steel props going across the site. This is a retaining wall on this side, this is a retaining wall on that side, and they're actually providing you with that support to your retaining wall. And that will again affect the actual mode of failure of your retaining wall, which we'll come back to. Alternatively, for wide excavations, you might have props which are raked or inclined, as indicated there. And these are even at these large steel props running from one side of the excavation to the other. Does that work? This is just an example of an anchor wall, a number of different techniques, but the main point to note there is there's a concrete section which is pressure grouted into the ground. You've got a strand running up here, and this is locked off at this point to provide you with that. Basically,
这为啥这样一打就毛过来了？
capacity to pull back your wall and provide you with that restraint. So this point to provide you with that basically capacity to pull back your wall and provide you with that restraint. So this is another typical example. Again, this is the row of anchors at this level. This is the row of anchors at this level. This is where the new woodside building is now being constructed. This is during construction, and that's a large raft foundation there. Okay, so obviously there's some aspects. A lot of the aspects in this unit, but in underground construction, there's a unit for in next year. Some of you might do it, which actually looks more in line with what construction practices need to be incorporated for all of these underground constructions. But the sort of main aspect you need to learn about in this unit is the wall stability. And there's two mechanisms, and I think I may have already talked about these mechanisms already. One is the cantilever method, cantilever wall. This is where we need to, we've got our embedded retaining. Remember, the ground level is here. Then we do an excavation. We'll say, for example, is to a depth H0, and we want to make sure our wall is stable under those conditions. And what do you think is actually providing the stability? What's providing the stability is actually the embedded length of the wall beneath the excavation side. So the longer this length of wall here, beneath this surface here, the more stable it is. And obviously, people don't want to actually need to put walls in longer than they need to be because to reduce costs. So you try and optimize this dimension here for your retaining wall to reduce that as much as possible. I'll come back to that in a second. And the other mechanism is the mechanism where you've got one prop or one anchor. And this is an example here. You've done an excavation. So you've installed your wall, the ground level is here. You've probably done a little bit of an excavation, maybe put in an anchor or a prop, and then completed the excavation depth.
Active. What? Passive. 怎么还是拉着它一样？
Down to some level here. Now in this situation here, the wall isn't rotating about some point of depth. That's the actual mechanism that's going to actually lead to a failure is one where you're actually rotating about the location of the anchor itself. Okay, so we now look at the first of those. It isn't rotating about some point of depth. That's the actual mechanism that's going to actually lead to a failure is one where you're actually rotating about the location of the anchor itself. Okay, so now look at the first of those mechanisms. So I may well have covered this a little bit already, I remember, but it doesn't really matter. We've got a cantilever wall. We've got our ground level here. We've installed our cantilever wall, which could be a steel sheet pile, could be a diaphragm wall, could be a spy wall, whatever. We've done some excavations, so we've excavated the ground here to some point here. And what's happened is the wall has tended to move out like this. And it's tending to rotate about some, let's draw this a little bit different. Sorry, put the point of rotation a bit further down. So imagine we've got some point here where obviously this depth, the embedment depth here, if you could imagine if the wall was only this long, this wall is probably going to fall over it. Yeah? So we've got some point of rotation here. What we're saying is we've got the soil is moving, the wall is moving away from the soil here. So we know that that's active pressure conditions at the limit. So it's going to drop and drop and drop, and it won't be able to drop any lower than the active limit. So we must know that we've got active stress conditions in this particular zone here. We also must know that as the wall is essentially falling into that, or being restrained by this ground here, and at the point where we're just about to fall over, the soil is giving as much as it possibly can in terms of resistance, and that resistance must equal to the passive stress. So we must be at our upper limit, maximum stress here, and lower limit here, at the point when it's just about falling over. So we get some rotation. In addition, we get some passive conditions below that point of rotation, and some active conditions on that side of our retaining wall. So we need to actually solve this problem. We would need to plot active and passive conditions on both sides of our retaining wall, and that's what standard software packages will perform. When you need to do calculations which are by hand or simplified calculations, what normally happens is we ignore everything below the point O, and let's write down here, ignore stresses point O, and is determine distance d for moment equilibrium. I'll come back to in a second. And choose below the excavation equal to 1.2 d. So this is the required wall penetration below excavation. So this is a simplification, and what we're doing is we're ignoring everything below the point O, but then we're allowing for the fact that we need to generate these active and passive minutes, otherwise we wouldn't get a rotation point occurring. And for horizontal equilibrium, we'll find that if we just chose the points above O here, we'll find we don't have our horizontal equilibrium, or active force and passive force will not equal to each other. So for the overall problem looks like this. So when we say moment equilibrium, what we're now assuming is we've got some point O here, and just for a simple time, we'll say we've got an active pressure distribution down to point O here, and we've got a passive pressure distribution here. So what we've got so-called F active, F passive. And if we have a very simple problem, the active force will act at the centroid of our triangular distribution, and for moment equilibrium, we just want this x1, that distance, and that distance x2. We require FA times x1 to be really less than or equal to FP times x2. So we want the restraining moment associated with passive force here to exceed the restraining moment associated with the active force. And so what we need to do is we determine D such that so that FA times x1 is equal to FP times x2. So just in page 55 of your course notes, there's an example 5.1 illustrating this application of exactly what I've just talked about, where we've got, in this case, we've got a 4 meter excavation, and we've got a deflected shape about some point O here. And again, what we're doing is we're just ignoring everything below this point O here, and we're just looking at the active pressure distribution and the passive pressure distribution. Now, in this case, the example is a dry sand. We've got no water pressures to consider. Yeah. No, it's not a factor of safety. It's actually a requirement to provide you with what you need to actually have a valid mechanism. You need to have, and to develop this point of rotation, you need to develop passive and active pressures below that point. So it's not actually a factor of safety. It's actually a requirement to be able to do that. I'll come back to in a second about how we determine the equilibrium, how we evaluate equilibrium in a minute. But essentially, that's really because of this. In reality, it doesn't happen. When you're engineers, you're just using software, and you actually allows for all passive and active. It's just really tedious to do this by hand. So that's the simplification you'll find in every textbook on this subject. So what I was going to say was that we've got no water pressures here, so we can calculate the value of the active pressure at point A here is equal to Ka times sigma v. This is a full equation, but U is equal. For the 0, sigma v dash at this depth here is equal to the active pressure at point A here is equal to Ka times sigma v. This is a full equation, but U is equal to 0. Sigma v dash at this depth here is equal to 4 plus d times the unit weight, where that's value of d. Similarly, point B here.
你他妈给 C 扔哪儿去了？
Here's the passive resistance. It's gamma times D is the vertical total stress. It's also equal to the vertical effective stress because U is 0. Complicate P. So now we know this value here. We determine the active force here by finding the area of those triangles, and then we take the moments about O, and we know this distance here is going to be 1/3 of the base of that triangle, which is 4 plus D divided by 3. And for at equilibrium, we have limiting equilibrium, where you're just at the point where the passive moment and active moment are equal, you'll find this here, we get P, and then we take the moments about O, and we know this distance here is going to be 1/3 the base of that triangle, which is 4 plus D divided by 3. And for at equal P, so now we know this value here, we determine the active force here by finding the area of those triangles, and then we take the moment about O, and we know this distance here is going to be 1/3 of the base of that triangle, which is 4 plus D divided by 3. And for at equilibrium limiting,
1/2底乘高，这个也是1/2底乘高。
in equilibrium, where you just at the point where the passive moment and active moment are equal, you'll find this here, you get a value of D. You get this equation here, it's a cubic equation, but normally you would just substitute in the various values. For our various values, here in this example, you'll find we need a depth of penetration below the excavation level of 3.7 meters for D, and therefore the penetration that we actually need for our wall for equilibrium to satisfy equilibrium is 4.44 meters for that particular example. If we look on, if we go to the last example probably for today, we look at example 5, maybe I'll see. Example 5.2 here again in your course notes. What we've got here is we've got an excavation where we've got two different materials. We've got sand overlying clay, and our excavation on one side of the wall is to 6 meters, so we've got a 6 meters excavation here. This is our wall here, and we've got a cantilever situation, so we're basically looking at the
短期的话，那就是不排水。
wall rotating about some point at depth. Now there's a couple of points here we need to think about. First of all, what we're asked here is to check the short-term stability for the 12-meter long wall. Now this comes back to what Sue just asked me there. Is the factor of safety about the extra length, etc. When you're actually evaluating the stability, you need to allow again for that value. So if we're saying in this particular example, we're told that the wall is extended a distance of 6 meters below the base of the excavation. When we're evaluating stability, we don't take moments about the bottom of the wall, because that's equal to essentially 1.2 times D. Yeah. So we need to now take this distance and this is our D value equal to 5 meters. So you might be asked in any particular problem, check to see if this wall is going to fall over. If it's a cantilever, you need to check, take moments about some points so that that point is such that it's 1.2 times its distance from the excavation level to that point is the overall length of the wall beneath the excavation. Okay, so that's point number one. Point number two is in all of these problems, we need to separate we need to draw separate diagrams for effective stresses, sigma HA, sigma HP, and water pressures. Sheet paper and use on the other side. So what's important about that? You see, in an exam situation, normally you're asked to determine the pressure distribution acting on your retaining wall. You need to go and realize that you need to actually calculate these numbers separately. You have two different diagrams, and then the total stresses is the total stresses on the active side is obviously the sum of both. So you take they're the forces that you use to calculate the actual stability, and on the passive side, obviously is equal to sigma HP plus U. And the reason for that is normally for problems involving seepage, which we're going to come back to again. But probably the first example we'll do on Wednesday morning will involve seepage. But it's a good practice to get into this. So what we in the example I'm just going to look at now, we've got sand layer here. We just ignore the presence of the clay for a minute. In the sand layer, we've got a sand layer there at a depth of 4 meters. We've got two diagrams. These are the effective stresses here on this diagram, and these are the water pressures on this diagram. The reason we always, when we're looking at seepage, but it's one of the areas that everybody, in textbooks even, get completely mixed up and confuse everybody. If you actually try and look at the problem involving effective stresses and water pressures, then you won't run into problems. So what we end up doing here, we've got a cantilever wall. So obviously on this in our sand here, we're going to be calculating the effective active stress, and we're going to be calculating the water pressures in that sand here. And that's absolutely fine. That's all we know. For example, we've been told we've calculated our Ka from the numbers we've been given here, and we've calculated the numbers, the water pressure. We're told the water level is at ground level, so this is the water level here, and the water pressure 4 meters depth is 40 kPa. Now what's the
Why does that affect your water?
funny about this particular diagram is that it's combining sand and clay. So in sand and clay, we don't need to draw separate diagrams because we know on the active side of the retaining wall, the total stresses is sigma V minus twice SU, and on the passive side, it's equal to sigma V plus twice SU. So what we've drawn here, we don't need therefore to draw any core pressures on this diagram. This is the number of core pressure diagram. But on this diagram here, what we're actually ending up plotting are total stresses. So these are total stresses in the clay. So what we're doing here in this calculation is, okay, we've calculated the sand active stresses, sigma Ka times sigma V dash minus 2C dash root K. And C dash is 0. What we're doing here in this calculation is the sand active stresses, sigma Ka times sigma V dash minus 2C dash root Ka, and C dash is 0. So it's just Ka times sigma V dash. Then we can see we're just on the junction here into a clay layer where the undrained shear strength of the clay is 30 kPa. So point C there, and you should work through this yourself, but point C would be equal to sigma V, the vertical total stress, plus twice the undrained shear strength. Which is 30. So that would be, in our example here, we've got a unit weight, what's the unit weight? Which is, you should work through this. Yourself. point C would be equal to sigma V, the vertical total stress, plus twice the undrained shear strength, which is 30. So that would be, in our example here, we've got a unit weight, that's unit weight. Unit weight is 20, and so at this point C, I'll just write, I must have, point C. Point C here is gamma H minus twice SU, so that's the total weight, vertical stress minus twice SU. Again, we're at active conditions. Down at this point, the rotation is going to be gamma H, which is the unit weight, times the depth, minus twice SU gives you point B. And point C, point E on this side is going to be gamma H plus twice times the depth, minus twice SU. Here is gamma H minus twice SU, so that's the total weight, vertical stress minus twice SU. At point D, we've got, again, we're at active conditions. Down at this point, just at the point of rotation, is going to be gamma H which is the unit weight times the depth minus twice SU gives you point D, and point C. Point E on this side is going to be gamma H plus twice SU, because that's sigma V plus twice SU is the expression for the passive stress on and total pressure at F. This is probably another area where people sometimes get confused. In a clay layer, even though you're at the surface, exposed to the atmosphere, even though gamma H is equal to 0, you've got plus the SU term still there. So you need to add plus twice SU to give you layer stress at that point F here. So what this just gives you, these problems can get incredibly tedious and complicated, which is why obviously it's much better to use a spreadsheet, much better to use a computer program. So very often in exam situations, they don't get you to do the equilibrium, look at the equilibrium for problems like this. I normally ask you to produce or predict distributions acting on the wall just about at the point of failure, and actually go and overall calculate the stability. Now in this case, we're looking at an example where we've got a pressure distribution here and here, and what you do is you take moments about 0.0 here, you have to divide all of your forces into different components, the triangle here and another one here. So you've got all of these forces here associated with those pressure diagrams, and then you take moments about O to see if you've got a stable situation. And that's what's been done here. And in this particular example, you have a stable situation because the moment about the zero, the point of rotation, is less than the passive moment, which is actually providing you with the restraining moment, preventing collapse. Okay, so I'll leave it at that for today. I know there's like everything, I'll give you.
哦，你的妈呀！我靠！先就这吧，慢，明天早上接着起来学。我他妈眼疼着，我操！连学他妈1个月，我操！我基本上没歇，天天鸡巴看他妈10几个小时的电脑，我靠，疯了！就这吧，拜拜。